Empty space is not empty at all. It is a seething ocean of energy, a reality that leads directly to the quantum vacuum catastrophe. This is not science fiction, but a genuine crisis at the heart of modern physics. By the end of this, you will understand why our universe should not exist according to our best theories, and what this means for the future of science itself. We will uncover why the void is alive with ghostly particles and how a single number threatens to tear apart our understanding of reality. What does true nothingness even mean anymore? For centuries, the void was considered the ultimate emptiness, a stage of perfect nothingness upon which the drama of the universe played out. This classical picture of a true vacuum is stark and silent. But quantum mechanics shatters this serene image entirely. In the quantum realm, what we call empty space is anything but empty. It is a vibrant, dynamic medium, a seething ocean of energy constantly in flux. This is the quantum vacuum. The energy that fills this vacuum is known as vacuum energy, or zero-point energy, a fundamental background hum that exists even at the unimaginable cold of absolute zero, the temperature where all classical motion is supposed to cease. This energy arises from a fundamental rule of the quantum world, the Heisenberg uncertainty principle. This principle tells us that on the tiniest scales, there is a fundamental limit to what we can know. We cannot precisely know both the energy of a system and the exact time of that energy measurement. This inherent fuzziness means that empty space cannot have exactly zero energy. Instead, it is a cauldron of temporary energy fluctuations. These brief borrowings of energy from the universe itself give birth to virtual particles, pairs of particles, and their antiparticles that flicker in and out of existence in an unimaginably short instant. Think of it like the surface of a calm ocean. From a distance, it appears flat and serene, but up close, you see it is actually a churning, turbulent soup of waves, currents, and unseen life teeming just beneath the surface. The quantum vacuum is exactly like that. Its apparent emptiness hides a frantic, bubbling activity that is the very fabric of spacetime. This foundational understanding of a space alive with invisible energy sets the stage for a profound conflict, a clash between our most brilliant theories and the stark reality we observe, a conflict that leads us directly to the edge of a cosmic catastrophe. This frantic energy of the vacuum demanded a new language, a new way to describe reality itself. That language was born from the minds of physicists grappling with the strange marriage of quantum mechanics and Einstein's theory of relativity. It evolved into quantum field theory, a framework so profound it redefined what a particle even is. The story of its development is a journey from confusion to breathtaking clarity. Paul Dirac was one of the first to glimpse this new reality. His equations for the electron predicted the existence of its antimatter twin, the positron, a discovery that forced physicists to reconsider the very nature of emptiness. Dirac proposed a radical idea, a sea of invisible, negative energy electrons filling all of space. What we perceive as empty space is just this sea, and a particle is a tiny ripple upon its surface. While his specific Dirac sea model was later refined, the core idea was revolutionary. Emptiness was not empty, it was a plenum, a foundation. Other pioneers built upon this, formalizing the concept of fields permeating all of space. Think not of particles as tiny, solitary balls, but as localized excitations like knots of energy in an invisible, universal fabric. There is an electron field stretching throughout the cosmos. Where it is calm and flat, we perceive nothing. but where it is vibrating or excited, we detect what we call an electron. The same is true for a photon field, a quark field, a Higgs field. Every fundamental particle has its own field. This is the heart of quantum field theory. The vacuum, then, is redefined. It is no longer a state of true nothingness. It is the ground state, the lowest possible energy configuration of all these fields. It is the quietest these fields can ever be, but in the quantum world, quiet does not mean silent. This ground state is still alive with the humming zero-point energy and the constant, brief flickering of virtual particle pairs. This sophisticated framework was a monumental achievement, perfectly describing the behavior of particles and forces. Yet, buried deep within its elegant mathematics lay a time bomb. The very definition of the vacuum as this energetic ground state would lead to a prediction so spectacularly wrong, it would threaten to unravel everything. These virtual particles are the ghosts haunting the vacuum. They emerge from the void as a particle and its antiparticle partner, exist for a vanishingly brief moment, and then annihilate each other, returning their borrowed energy to the universe. This entire process is governed by a subtle but powerful rule, the energy-time uncertainty principle. It states that for an extremely short period, the universe cannot strictly enforce the conservation of energy. Think of it as a cosmic loan. The vacuum can borrow a tiny amount of energy, but it must pay that loan back almost instantly. The more energy it borrows, the faster it must be repaid. This is why these particle pairs are virtual. They are a temporary fluctuation, a fleeting ripple in the fields that make up reality, never lasting long enough to be directly observed. Their existence, however, is far from just a theoretical curiosity. We can witness their ghostly handiwork in a beautiful and tangible experiment known as the Casimir effect. Imagine two perfectly smooth, uncharged metal plates placed incredibly close together in a perfect vacuum. Outside the plates, the quantum vacuum is a bustling metropolis of virtual particles of all possible wavelengths, constantly flickering into being. But in the narrow gap between the plates, only certain wavelengths can fit, like how only specific musical notes can resonate inside a flute. This restriction means that fewer virtual particle pairs can pop into existence in the gap compared to the bustling activity outside. The result is a subtle but measurable pressure. The greater number of virtual particles pushing on the outer surfaces of the plates compared to the fewer particles pushing from within the gap forces the plates together. We can literally see these two metal plates click together, driven by nothing but the restless energy of empty space. This is not a thought experiment. It has been confirmed in laboratories. The Casimir effect is direct physical proof that the quantum vacuum is real, that these virtual ghosts have a tangible push and pull on our world. If such a subtle effect can move metal plates, it forces us to ask a staggering question. Just how much raw, untapped energy is simmering in every cubic centimeter of the void around us? The answer to that question is where our story takes a truly catastrophic turn. So how do we measure the energy of this ghostly sea? We start with one of the simplest systems in quantum physics, a tiny mass on a spring, a harmonic oscillator. In our everyday world, such a system can be completely still, its energy at zero. But in the quantum world, the uncertainty principle forbids this perfect stillness. The oscillator always has a minimum jitter, a fundamental vibration called the zero-point energy. It can never be completely turned off. Now, we take this simple, undeniable fact and scale it up to the entire universe. According to quantum field theory, every point in space is filled with these oscillators, one for every possible type of fundamental field and for every possible frequency or wavelength at which that field can vibrate. To find the total vacuum energy in, say, a single cubic centimeter of space, you would theoretically have to add up the zero-point energy from every single one of these countless oscillators. You sum the energy from all the low-frequency waves, the radio wave equivalents of the quantum fields, then add in the energy from all the higher frequencies, the microwave, infrared, visible light, and on, up to the highest possible frequencies far beyond gamma rays. This is where the calculation breaks from being difficult and becomes absurd. When you perform this sum over all possible frequencies, the result isn't just large, it is catastrophically infinite. Of course, physicists know that at some incredibly small scale, new physics must come into play, putting a cap on the highest possible frequency. So they apply a reasonable cutoff, a point where our current theories are no longer valid. Even with this conservative limit, the number that emerges is beyond human comprehension. The energy density predicted for empty space is a 1 followed by 112 zeros. This isn't just a big number, it is a number so immense that the energy in a single coffee mug would be enough to boil every ocean on Earth into steam instantly. This calculation is not controversial. It is a straightforward, almost elementary consequence of our most successful physical theories, and it is utterly, undeniably wrong. This mathematical result is an ultraviolet catastrophe for the vacuum itself. The sum of all those zero-point energies doesn't just give you a big number, it gives you an infinity. The calculation tells us that the energy density of empty space should be infinitely large. This is a physically nonsensical answer, a clear sign that our theory, despite its incredible successes, has hit a fundamental wall when confronted with the void. To make any progress at all, physicists had to develop a brilliant, if slightly unsettling, mathematical workaround known as renormalization. The core idea is to tame the infinity. When calculating the outcome of a particle interaction, you often get these infinite terms popping up from the vacuum's boundless energy. Renormalization is a procedure that systematically identifies and subtracts these infinities, allowing the finite, physically measurable results to shine through. Think of it like a digital photo editor removing background noise from a priceless image. The editor isn't changing the subject of the photo. They are just filtering out the static that the camera itself introduced, revealing the clear picture beneath. Renormalization does exactly this for quantum field theory. It subtracts the infinite vacuum noise, and what remains are predictions of stunning accuracy, like the magnetic properties of the electron, which have been verified to within 1 part in a trillion. It is arguably the most successful mathematical trick in the history of science, but a trick is what it remains. Renormalization does not solve the underlying problem, it merely sidesteps it. The procedure successfully sweeps the infinity under the rug, allowing us to use the room. We can now make perfect predictions about what happens inside the room, but we are all standing on a rug that is bulging with a problem we can no longer ignore. The vacuum energy is still there, infinite and unexplained, a foundational crack in our understanding of the universe. The mathematical trick of renormalization had swept the infinity under the rug, but the rug was now beginning to bulge. This hidden energy of the vacuum was about to collide with the largest theory of all, Albert Einstein's general relativity. In 1917, Einstein was applying his magnificent new equations to the entire cosmos, and he encountered a problem. The universe he saw through his equations was dynamic, either expanding or contracting under the relentless pull of gravity. Yet, the scientific consensus of his time insisted the universe was static and eternal. To reconcile his theory with this belief, Einstein made a small but profound adjustment. He introduced a new term into his equations, a fudge factor he called the cosmological constant. This constant represented a uniform energy density inherent to the fabric of space itself, a kind of anti-gravity, a repulsive force that would perfectly balance gravity's inward pull on the largest scales, freezing the cosmos in a state of permanent equilibrium. It was a static universe by design. A little over a decade later, Edwin Hubble's observations of receding galaxies shattered this static model. The universe was not standing still, it was flying apart. With this definitive evidence, Einstein reportedly discarded his cosmological constant, calling it his greatest blunder. He had missed the chance to predict the expanding universe. The constant was removed from the textbooks, a curious historical footnote, but the story was far from over. Decades later, observations of distant supernova revealed something even more shocking. The expansion of the universe is not slowing down due to gravity, as everyone expected. It is accelerating. Something is pushing the galaxies apart faster and faster. And the leading explanation for this mysterious repulsive force, this dark energy, is none other than Einstein's long-abandoned cosmological constant, resurrected from the history books. The energy of empty space itself could be the engine driving the cosmic acceleration. This is the crucial link that creates our catastrophe. The quantum vacuum energy, that seething ocean of virtual particles, should naturally manifest as a cosmological constant. The energy of nothing should be shaping the fate of everything, and when we compare the two, the theoretical prediction from quantum field theory and the observed value from cosmology, we are not just a little bit off. We are confronted with the most spectacular failure of prediction in the entire history of science. So we arrive at a number, a figure so vast it defies all human intuition. To calculate the energy density of the quantum vacuum, physicists turn to the Planck scale, the absolute limit where our current understanding of space and time is believed to break down. This is the highest energy scale where our theories are still thought to have any validity. The calculation itself is straightforward, a direct consequence of the quantum fields that fill every point in space. And the result is approximately 10 to the power of 112 joules per cubic meter. Let us try to grasp the sheer scale of this number. A joule is a modest unit of energy, roughly the amount it takes to lift a small apple 1 meter against Earth's gravity. Now, imagine compressing 10 to the 112th power of those joules into a single cubic meter of space, a volume no bigger than a small box. This is the theoretical energy that our best physics says should be boiling inside every single speck of the void around you. This number is so colossal that the energy contained within the volume of a single coffee cup would be more than enough to instantly vaporize every ocean, every lake, and every drop of water on our entire planet. It is a figure of unimaginable destructive potential, a constant, seething storm contained within what we perceive as utter stillness. This is the universe as it should be according to quantum field theory. Yet we are here in a stable cosmos, surrounded by a vacuum that feels, for all practical purposes, perfectly empty. This is the first prediction, and it stands in stark, violent opposition to the reality we actually observe. Our universe holds a secret, a force so subtle it was hidden for almost all of human history. In the late 1990s, two independent teams of astronomers were studying distant stellar explosions known as Type 1, a supernova. These cosmic beacons have a known intrinsic brightness, allowing scientists to measure their distance with incredible precision. By observing how much the light from these supernovae was stretched or redshifted, they could also determine how fast the universe was expanding when that light was emitted billions of years ago. The researchers expected to find that the expansion of the cosmos was slowing down, gradually braked by the collective gravity of all the matter in the universe. What they found was the exact opposite. the data revealed that the expansion is not slowing at all, it is speeding up. The galaxies are flying apart faster today than they were in the distant past. This discovery was so shocking and profound that it earned the teams the Nobel Prize in Physics in 2011. The universe was being pushed apart by a mysterious, repulsive force, a phenomenon we now call dark energy. This was the resurrection of Einstein's cosmological constant, not as a fudge factor for a static universe, but as the dominant energy shaping our cosmic fate. Subsequent missions, like the magnificent Planck satellite, have mapped the cosmos with painstaking detail, allowing us to measure the strength of this dark energy with stunning accuracy. The energy density required to drive this accelerating expansion is precisely quantified. It is approximately 10 to the power of -9 joules per cubic meter. This is the number we actually observe. Now, place that observed value next to the theoretical prediction from the quantum vacuum. On one side, we have the colossal theoretical prediction of 10 to the 112 joules per cubic meter. On the other, the whisper-quiet observed value of 10 to the -9. The discrepancy between them is not a simple factor of 2 or 10 or even a million. It is a factor of 10 to the 121st power. This number is so vast it has no name, no analogy in the physical world. It is the largest mismatch between theory and observation in the entire history of science. The vacuum should be roaring with a ferocious energy that rips the cosmos to shreds in an instant, yet we measure only the faintest, most gentle of pushes. This is not a small error to be corrected. It is a chasm of misunderstanding so deep it calls into question our most fundamental ideas about reality itself. The numbers tell a story of profound confusion. On one side, a theoretical storm of 10 to the 112 joules in every cubic meter. On the other, the faintest cosmic whisper, an observed value of just 10 to the -9. The gulf between them is a factor of 10 to the 121st power. To grasp the sheer magnitude of this error, picture the entire observable universe, every galaxy, every star, every planet, all the space in between, filled completely with water. This unimaginable volume represents the vacuum energy our theories predict. Now, take the tiny, observed amount of dark energy we actually detect. In our analogy, that real energy would be smaller than a single proton floating within that universe-sized ocean. The difference in scale is not just large, it is incomprehensible. This is not a minor miscalculation to be fixed with a tweak to an equation. This is the worst theoretical prediction in the entire history of physics. It is the quantum vacuum catastrophe laid bare, a chasm of misunderstanding so vast it challenges the very foundations of our knowledge. How could our two most powerful and successful theories, quantum field theory and general relativity, be so spectacularly, undeniably wrong about the energy of nothing? The silence of empty space is screaming a mystery we have yet to solve. This staggering mismatch is far more than a simple math error. It represents a fundamental crack in the very foundation of physics. We are not just a little bit wrong, we are catastrophically wrong about the energy content of nothing itself. This discrepancy points to a deep, unresolved conflict between our two greatest descriptions of reality. On one hand, we have quantum field theory, which describes the microscopic world of particles and forces with breathtaking precision. On the other, we have Einstein's general relativity, which masterfully depicts gravity as the curvature of spacetime on cosmic scales. Both theories are monumental achievements, yet they speak completely different languages when it comes to the vacuum. The catastrophe reveals that we do not understand how gravity couples to the quantum world. According to our best quantum calculations, the vacuum energy should produce a gravitational effect so immense it would curl the universe into a microscopic knot in a fraction of a second. The fact that we see a universe that is largely flat and gently accelerating means something is profoundly missing. There are only a few equally unsettling possibilities. Perhaps our theory of the quantum vacuum is drastically incomplete, and we are misunderstanding the nature of empty space in some fundamental way. Maybe Einstein's theory of gravity, for all its glory, breaks down on the largest scales or in the face of vacuum energy. Or, most likely, both of our magnificent theories are merely approximations of a deeper, more complete truth we have not yet discovered. This is not an isolated puzzle for specialists to solve in a back room. The quantum vacuum catastrophe strikes directly at the heart of the greatest quest in modern physics, the dream of a theory of everything. For decades, the ultimate goal has been to weave quantum mechanics and general relativity into a single, seamless fabric, a framework often called quantum gravity. This would be the final theory, one that could describe every force and particle from the first moment of the Big Bang to the silent end of the cosmos. But the vacuum catastrophe stands as a colossal roadblock on that path. How can we hope to unify our understanding of reality when our two pillar theories cannot even agree on the energy of empty space? The silence of the void is not just a mystery, it is a glaring signpost pointing to a hidden continent on the map of physics. We are missing a crucial piece, a principle so fundamental that without it, a complete picture of our universe will forever remain out of reach. Faced with this glaring contradiction, physicists began a desperate search for a solution, a mechanism that could tame the vacuum's ferocious energy. One of the most elegant and promising ideas to emerge was a concept known as supersymmetry. This theory proposes a deep and beautiful symmetry woven into the very fabric of reality, a partnership between the two fundamental classes of particles. On one side, you have fermions like electrons and quarks, the building blocks of matter. On the other, you have bosons like photons and gluons, the force carriers that transmit interactions. Supersymmetry suggests that for every known fermion, there exists a bosonic superpartner, and for every known boson, a fermionic superpartner. An electron would be paired with a hypothetical selectron, a photon with a photino, a quark with a squark. In this perfectly symmetric world, these superpartners would possess identical masses and charges. The magic of this pairing lies in their contributions to the vacuum energy. Calculations show that fermions and bosons contribute to this energy with opposite signs. Think of it like a perfectly balanced set of scales. On one side, the fermions push the energy in a positive direction with a certain force. On the other side, the bosons push with an equal and opposite negative force. In an unbroken, perfect supersymmetric universe, these two opposing contributions would cancel each other out with exquisite precision. The positive and negative would sum to exactly zero. The vacuum energy would vanish, the cosmological constant would be zero, and the catastrophe would be elegantly resolved. The roaring energy of the void would be silenced by a cosmic symmetry. This is the promise of supersymmetry, a theoretical fix of profound beauty, but nature, it seems, is not so perfectly symmetrical. If supersymmetry were unbroken, we should have detected these superpartner particles long ago. They would have the same mass as their familiar counterparts. We would see selectrons with the mass of electrons, photinos with the mass of photons. Our most powerful particle colliders, like the Large Hadron Collider, have searched tirelessly for any sign of them. So far, they have found nothing. This means that if supersymmetry is a real feature of our universe, it must be a broken symmetry. The superpartners are not missing. They are just incredibly heavy, existing at energy scales far beyond our current reach. This breaking of symmetry, while saving the theory from immediate falsification, shatters the perfect cancellation needed to solve the vacuum catastrophe. The scales are no longer balanced, the positive and negative contributions no longer sum to zero, leaving behind a small but non-zero remnant of vacuum energy. While this remnant could be vastly smaller than the original catastrophic prediction, it still does not naturally give us the incredibly tiny, positive value we actually observe. The beautiful solution remains just out of reach, a ghost of a theory haunting the edges of our understanding. Supersymmetry was not the only grand idea to confront the vacuum's fury. Another candidate, far more radical, stepped onto the stage: string theory. This framework proposes that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy, strings. The vibration of a string determines the properties of the particle it manifests, much like a vibrating violin string produces different musical notes. This elegant idea promised to finally unify gravity with quantum mechanics, to be the theory of everything. And with this new vision of reality came a new and startling vision of the vacuum. String theory does not predict a single, unique universe. Instead, it describes a colossal cosmic terrain known as the landscape, a vast multitude of possible stable vacuum states. Think of it not as one universe, but as a near-infinite archipelago of universes, each island with its own distinct physical laws and constants. In one pocket of this landscape, the strength of electromagnetism might be slightly stronger. In another, the mass of the electron might be different. Crucially, each of these vacuum states also possesses its own specific value for the cosmological constant, its own inherent energy of empty space. The values are not determined by a single elegant equation, but are scattered across a staggering range, from the catastrophically large numbers predicted by quantum field theory down to zero and even into negative values. In this picture, our universe is not special. It is simply one pocket among an almost endless sea of possibilities. It just happens to be a pocket where the cosmological constant is an exceptionally small, positive number, the whisper-quiet value of 10 to the negative 9 that we observe. This is where a controversial yet compelling line of reasoning enters the picture: anthropic reasoning. The argument goes that only in such a rare universe, with a vacuum energy so minuscule, could gravity slowly pull matter together over billions of years to form galaxies, stars, planets, and eventually us. In the overwhelming majority of other pockets in the landscape, the cosmological constant is either so massively positive that it rips spacetime apart before any structure can form, or so negative that the universe instantly recollapses into a big crunch. We could not possibly find ourselves living in those universes. Our existence as observers automatically selects for a universe capable of hosting life. This offers a potential, if deeply unsettling, explanation for the vacuum catastrophe. There is no fundamental reason our vacuum energy is small. We just got lucky. We live in one of the very few habitable corners of a vast cosmic multiverse. Yet, this solution comes at a profound cost. The string theory landscape and its anthropic reasoning are, for now, completely untestable. We have no way to probe these other universes, no experiment to confirm the landscape's existence. For many physicists, accepting an explanation that cannot be falsified feels like a retreat from the core mission of science, which is to find fundamental, testable reasons for why the universe is the way it is. The catastrophe, therefore, remains entirely unresolved, a stark reminder of the limits of our current knowledge and a beacon pushing us toward a deeper, more complete truth. This profound mismatch has a name: the cosmological constant problem. It is crucial to distinguish it from other cosmic mysteries, like the puzzle of dark matter. Dark matter is the search for an unknown type of matter that exerts gravitational pull, helping to hold galaxies together. The cosmological constant problem is fundamentally different. It is a crisis of energy, not matter. It asks why the energy inherent to empty space itself has the specific, minuscule value that we measure. The heart of the problem lies in a concept physicists call fine-tuning. Think of a radio dial with numbers ranging from 0 up to 10 to the 112. The dial represents all the possible values the vacuum energy could have taken. The vast, overwhelming majority of settings on this dial would result in a universe that is instantly and catastrophically uninhabitable. If the dial were turned even a fraction higher, the repulsive force would be so violent that galaxies, stars, and planets could never coalesce. The universe would be a thin, expanding gas ripped apart before any structure could form. If the dial were turned slightly into the negative, the universe would have collapsed back on itself in a big crunch almost immediately after it was born. Yet our dial is not set to 0. A value of exactly 0 might be explained by a beautiful, fundamental symmetry in the laws of physics, a perfect balance that cancels everything out to nothing. But that is not our universe. Our dial is set to an infinitesimally small positive number, 10 to the negative 9. It is a value so close to 0 that it allows the universe to expand gently for billions of years, permitting just enough structure to form for life to emerge, but it is not 0. This exquisitely precise, non-zero setting is what baffles scientists. Why this number? Why is the energy of the void so perfectly calibrated to allow for our existence? This is not just a puzzle, it is considered the most severe naturalness problem in all of fundamental physics. It is a constant, quiet reminder that our most brilliant theories are still missing a vital piece, a principle that can explain why our cosmos is so perfectly, delicately poised on a razor's edge. Perhaps the cosmological constant is not the final answer. Another possibility is that dark energy is not a fixed feature of empty space, but something that flows and changes, a cosmic weather pattern shifting over billions of years. This idea is known as quintessence, named for the fifth element of ancient philosophy, a substance beyond the ordinary matter of earth, air, fire, and water. Quintessence proposes that a new, dynamic energy field permeates all of space. Unlike the static cosmological constant, which assigns a single, unchanging value to the energy of the vacuum, a quintessence field can evolve. Its energy density can be high in one cosmic era and lower in another. It can, in theory, clump and vary across space, a subtle texture in the fabric of the cosmos. This dynamism offers a potential explanation for one of the deeper puzzles in modern cosmology: why the accelerated expansion of the universe is a relatively recent development in cosmic history. For most of the universe's life, gravity dominated, slowly pulling matter together to form galaxies and clusters. Only in the last several billion years did dark energy begin to overpower gravity and take control of the cosmic expansion. A quintessence field could naturally account for this timing. Imagine a field that was once weak and dormant, its energy diluted by the dense, young universe. As the cosmos expanded and thinned out, the field could have awakened, its repulsive force gradually growing until it became the dominant power we observe today. This is an elegant narrative, shifting the problem from explaining a single, mysteriously small number to understanding the behavior of a new cosmic actor. Yet for all its appeal, quintessence does not solve the core catastrophe. It merely repackages the mystery. We are no longer asking why the cosmological constant is so small. Instead, we are asking why the properties of this new quintessence field are so exquisitely tuned to produce the same whisper-quiet effect we see today. The fundamental problem of fine-tuning remains, simply transferred from a constant number to the initial conditions and potential of a field. The vacuum energy discrepancy, the chasm between quantum prediction and cosmic observation, still yawns wide open, untouched by this new layer of complexity. This fundamental deadlock between theory and observation is matched by a profound experimental challenge. We are trying to measure a ghost, while we can see the shadows it casts, as with the Casimir effect or the subtle shift in atomic energy levels known as the Lamb shift. Grasping the ghost itself remains utterly beyond our reach. These laboratory effects are like seeing the ripples from a stone thrown into a pond. We can study the ripples in exquisite detail, but we have no way to dive down and retrieve the stone. The stone, in this case, is the raw energy density of the quantum vacuum. The numbers we calculate from quantum field theory are for the energy at a single point in space, a volume of zero size. But our experiments can only ever probe an average over a finite volume, a space large enough to contain countless virtual particles flickering in and out of existence. The infinities predicted by the theory are smoothed out by the very act of measurement, leaving us with the faint, integrated signal we can actually detect. It is like trying to measure the precise height of every single blade of grass on a vast prairie from an airplane flying miles above. You might get a very good average height, but you will have completely missed the intricate, chaotic forest of individual blades right at your feet. This is the core of the measurement problem. Our tools are too blunt to probe the violent, microscopic reality of the vacuum. They can only register its gentlest, large-scale echoes. This forces us to look to the largest laboratory of all, the cosmos itself. The accelerating expansion of the universe, driven by dark energy, is our only direct, empirical window into the vacuum's energy. That whisper-quiet value of 10 to the negative 9 joules per cubic meter is not something we measured in a beaker on a lab bench. It was deduced from the redshift of ancient starlight across billions of light years. We are using the entire observable universe as our experimental apparatus. This creates a frustrating impasse. The proposed solutions, from supersymmetry to the string theory landscape, are breathtaking intellectual constructs. Yet they float in a realm of pure theory, largely untethered from the hard data that could confirm or refute them. Without a way to directly probe the quantum vacuum and measure its properties in a terrestrial lab, these ideas lack the crucial pressure of experimental evidence that has always guided physics forward. Breaking this deadlock will require something truly revolutionary, either a theoretical leap that redefines the vacuum in a testable way, or an experimental method of such exquisite sensitivity that it can finally listen to the faint, true hum of empty space. This fundamental challenge to our physics is also a direct assault on our philosophy. The quantum vacuum catastrophe forces us to confront a deceptively simple question: what is nothing? For millennia, human intuition has painted a clear picture. Nothing is the absolute void, a complete and total absence of anything, a stage of perfect blackness and silence before the actors of matter and energy arrive. This is the classical nothing, the idea that has shaped our language and our deepest thoughts about existence. But the seething quantum vacuum shatters this serene image into a million pieces. If what we call empty space is a vibrant medium of fluctuating energy, a factory for virtual particle creation, then the very category of nothing begins to collapse. The line between something and nothing blurs into obscurity. Is a virtual particle that exists for a fleeting moment something or nothing? It borrows its being from the universe itself, leaving a tangible push on metal plates in a lab. How can we call that nothing? This is not just a semantic game, it is a profound ontological crisis, a challenge to our understanding of what it means to be. The catastrophe suggests that our intuitive idea of a void is a grand and persistent illusion. Perhaps true nothingness, in the classical sense of a total absence of energy, fields, and potential, is not just rare but physically impossible. The universe seems to abhor a true vacuum. It appears that existence itself is the default state, a dynamic and eternal plenum where something, however subtle, is always happening. The ground of being is not a silent stage but a perpetual low hum. This leads to a staggering possibility that the cosmos we inhabit, with all its galaxies and life, did not emerge from a state of absolute nothingness, but from a pre-existing quantum state where the potential for everything was already woven into the fabric of reality. The Big Bang may not have been a sudden eruption from utter void, but a phased transition within an eternally active quantum realm. Our entire cosmic story, from the first second to the present day, might be unfolding within an infinite ocean of latent energy, a something that we have mistakenly been calling nothing all along. This quiet hum of the vacuum is not just a scientific curiosity, it is the author of our cosmic destiny. The precise value of this energy, that whisper of 10 to the negative 9, is the single most important factor determining how the entire story of the universe will end. With a cosmological constant we have observed, a small, positive number, the future is written in the cold, silent script of eternal expansion. This is the fate known as the heat death. Over trillions upon trillions of years, the acceleration will continue to mount. Galaxies beyond our own local group will be pushed away from us at speeds faster than light, their light fading from view forever. The stars will slowly burn out one by one, their furnaces extinguished. Black holes will evaporate over unimaginable timescales through Hawking radiation. The universe will become a vast, ever more dilute and freezing sea of isolated particles and radiation, drifting endlessly apart in an ever-cooling, darkening void. It is a slow, gentle, but ultimately absolute end. Yet our universe is perched on a razor's edge. This future is only possible because the vacuum energy is so incredibly small. If it were just a few dozen times larger, still an infinitesimal fraction of its predicted theoretical value, the outcome would be far more violent and swift. This is the scenario of the Big Rip. A stronger dark energy would not just accelerate the expansion between galaxies, it would eventually overcome all other forces. First, galaxy clusters would be torn apart, then individual galaxies. As the repulsive force grows, it would rip stars from their solar systems. In the final, horrifying moments, it would overcome the electromagnetic forces holding atoms together, shredding every molecule, every atom, and finally, the very fabric of spacetime itself. The universe would end in a catastrophic, instantaneous unraveling. The fact that we do not live in a Big Rip universe, that we instead have a cosmos that persists for billions of years, allowing for the formation of galaxies, stars, planets, and life, is not a coincidence. It is the most profound fine-tuning imaginable. The vacuum energy dial is set to a value that permits a long, rich, and structured cosmic story, a story that includes us as observers. This connection between the energy of nothing and the potential for life adds another, deeply philosophical layer to the catastrophe. We are not just trying to solve a math problem, we are trying to understand why the universe is so perfectly, delicately calibrated for existence. This vacuum catastrophe is not a lonely anomaly in the theoretical landscape. It has a formidable twin, another profound mystery that points to the same unsettling gap in our understanding, known as the hierarchy problem. While the cosmological constant problem asks why the energy of empty space is so tiny, the hierarchy problem asks why the fundamental forces of nature have such wildly different strengths. Specifically, it focuses on the puzzling gap between the electroweak scale, the energy at which the electromagnetic and weak nuclear forces unite, and the Planck scale, that ultimate limit of our physics. The electroweak scale is about 250 times the mass of the proton, a realm we can probe with our particle colliders. The Planck scale, by contrast, is a staggering 10 to the 16th power times larger. This is not just a big gap, it is a chasm of magnitudes. The problem becomes acute when we consider the Higgs field, the entity that gives other particles their mass. The mass of the Higgs boson itself is incredibly sensitive to these ultra-high energy scales. Through quantum corrections, virtual particles flitting in and out of existence should drag the Higgs mass up to the Planck scale, making it enormously heavy. This would mean that the electroweak force, and by extension all the atomic structures we know, should be unimaginably stronger than they are. Our reality should look completely different. Yet, the Higgs mass we actually measured is light, sitting comfortably at the electroweak scale. This means its enormous quantum corrections must be cancelled out by an opposing, equally enormous effect with exquisite, almost impossible precision. It is an unbelievable balancing act, a fine-tuning so severe it seems like a cosmic miracle. Both the hierarchy problem and the vacuum catastrophe are, at their core, crises of naturalness. They are both screaming that our theories are producing numbers of an absurd, unnatural size, numbers that require an inexplicable and perfect cancellation to match the gentle, structured universe we observe. This is the crucial link. These are not two separate puzzles, they are likely two different symptoms of the same underlying disease in our foundational physics. The same missing principle that explains why the vacuum energy is a whisper might also explain why the Higgs boson is so surprisingly light. They are twin beacons, both shining a light on the same hidden shore. This connection transforms the vacuum catastrophe from a curious and isolated failure into a profound clue. It suggests that a deeper theory, one that successfully unites quantum mechanics and gravity, will not solve just one of these problems. It will solve them both because they are fundamentally the same problem, a single flaw in our vision of reality seen from two different angles. The silence of the vacuum and the surprising lightness of the Higgs are two voices asking the same unanswered question. Gravity is the silent, missing actor in this cosmic drama. While the quantum world buzzes with the frantic energy of the vacuum, this energy remains almost entirely invisible to the forces that govern the small scale. In particle physics experiments, the colossal vacuum energy is completely ignored, and for good reason. It simply does not interact through the electromagnetic force or the strong or weak nuclear forces. You can build the most powerful particle collider in the world, and this background hum of the universe will not affect your results in any measurable way. It is a ghost that passes through the walls of your detector without a trace. This is why quantum field theory gets away with its sweeping infinity under the rug of renormalization. For all particle interactions except one, the vacuum energy is an irrelevant constant, a background noise you can subtract without changing the music. But there is one force that hears this ghost, one force that must listen to the hum. That force is gravity. Einstein's theory of general relativity delivers a clear and non-negotiable decree: all energy curves spacetime. It does not matter if that energy is the bright light of a star, the silent mass of a planet, or the fleeting flicker of a virtual particle. Energy is energy, and gravity must respond to it. The vacuum energy, therefore, cannot be ignored by the cosmos. Its immense theoretical density should be warping the fabric of reality into a tightly curled knot, creating a universe that is microscopically small and unimaginably violent. The fact that we see a vast, gently accelerating cosmos means the gravity we experience is not responding to the vacuum energy, in the way our theories insist it should. This is the heart of the catastrophe. We have two sets of rules. The quantum rulebook tells us the vacuum energy is astronomically large. The general relativity rulebook tells us that such a huge energy must produce an equally astronomical gravitational effect. Yet when we look at the universe, we see a gravitational effect that is almost zero. The two rulebooks are fundamentally incompatible on this point. We are trying to plug a number from one theory directly into another theory, and the result is a physical impossibility. This failure is not a flaw in either theory individually, but a screaming signal that we are missing the unified rulebook, the theory of quantum gravity. We do not understand how gravity behaves when it is coupled to the quantum foam, to the seething, probabilistic world of the vacuum. The vacuum catastrophe is therefore the most direct and urgent consequence of our failure to unite our understanding of the very large with the very small. It is the universe's way of showing us, in the starkest terms possible, that a piece of our fundamental picture of reality is not just missing, but that we are trying to force two mismatched pieces together. The silent tension in empty space is the precise point where our two greatest theories collide, and where our future understanding of the cosmos will be born. This catastrophe did not arrive unannounced. Its ghost was glimpsed decades before the problem had a name, a warning whispered by one of the sharpest minds in physics. In the 1920s, Wolfgang Pauli, the brilliant and notoriously critical physicist, was already wrestling with the implications of the newly formulated zero-point energy. He performed a simple, back-of-the-envelope calculation, estimating the gravitational effect of this vacuum energy. His conclusion was stark. If the zero-point energy of the radiation field were real, and if it truly did curve spacetime as Einstein's theory demanded, then the entire observable universe would be curled up into a sphere smaller than our solar system. The cosmos as we know it could not exist. Pauli, confronted with this absurd result, did what seemed logical at the time. He dismissed it. He concluded that such a gravitational effect was clearly nonsensical, and therefore the zero-point energy, while mathematically present in the equations, must be nothing more than a formal curiosity without physical reality. It was a reasonable assumption, but a fateful one. The clue was there, and it was ignored. Why did it take so long for this buried seed to grow into a full-blown crisis? The answer lies in the fragmented nature of scientific progress. Throughout the middle of the 20th century, physics advanced on two separate fronts. On one side, quantum field theorists were perfecting their description of the subatomic world. They encountered the infinities of vacuum energy, but they developed the powerful tool of renormalization to sidestep them. For their purposes, the vacuum energy was an unobservable background constant, a number you could subtract away. It had no bearing on the particle collisions they were studying. On the other side, cosmologists were applying general relativity to the universe at large. They had discarded Einstein's cosmological constant and were building models of an expanding cosmos dominated by matter and gravity. The two communities were speaking different languages and asking different questions. The quantum physicists saw no need to worry about the gravitational consequences of a vacuum energy they could mathematically ignore. The cosmologists saw no need to introduce a mysterious energy field when the universe seemed to be explained by matter and expansion alone. The catastrophic connection between them remained invisible, a bridge that nobody thought to build. It was only when these two rivers of thought finally converged, forced together by the shocking observation of cosmic acceleration in the late 1990s, that the problem erupted into view. The discovery of dark energy was the key that unlocked the hidden room. It proved that the vacuum energy was not just a mathematical artifact, It was physically real and shaping the fate of the cosmos. Suddenly, Pauli's dismissed calculation was no longer a curiosity, it was a prophecy. The problem had been hiding in plain sight for 70 years, waiting for the moment when our observations of the universe would finally force us to listen. This history is a powerful reminder that our biggest breakthroughs often come not from new data alone, but from connecting old ideas in new ways, from building bridges between islands of knowledge that were thought to be separate. The silent paradox of the vacuum has mobilized a global scientific campaign, a quiet hunt for clues unfolding in colossal machines and deep space observatories. Beneath the Swiss-French border, the Large Hadron Collider runs a relentless interrogation of reality, its proton beams colliding at energies that recreate the universe's first moments. Here, physicists search for the faintest traces of supersymmetry, for any deviation from the standard model that could hint at a hidden particle sector capable of taming the vacuum's ferocious energy. Every new dataset is scrutinized for a selectron, a photino, a squark, any signature of the symmetry that could balance the cosmic scales. So far, the vacuum has not given up its secret partners, but the search continues, pushing the machine's capabilities to their absolute limits, probing ever higher energies for the new physics that must be lurking somewhere. While one frontier lies deep underground, another stretches across the cosmos. High atop mountains and now flying in space, a new generation of astronomical instruments is turning its gaze to the dark energy enigma. The Dark Energy Spectroscopic Instrument, DESI, is meticulously mapping tens of millions of galaxies and quasars, constructing a three-dimensional cosmic map of staggering detail. Its goal is to trace the history of the universe's expansion with a precision never before achieved, watching for any subtle change in the strength of dark energy over billions of years. Is it truly a constant, as Einstein proposed, or is it dynamic, a quintessence field slowly evolving? Simultaneously, the Euclid Space Telescope is now peering into the deep dark, its sensitive optics designed to measure the shapes and distances of billions of galaxies. By observing how the immense gravity of dark matter clusters warp the light from these distant galaxies, a phenomenon known as weak gravitational lensing, Euclid will provide an independent, exquisitely precise measurement of how dark energy has fought against gravity to shape the cosmic web. These are not just telescopes, they are time machines gathering ancient light to read the diary of the vacuum's influence across cosmic history. No single experiment is expected to solve the vacuum catastrophe outright. These monumental efforts serve a more immediate and perhaps more crucial purpose. They are fencing in the possible. Every null result from the collider narrows the territory where supersymmetric particles can hide, forcing theorists to refine their models. Every precise data point from DESI and Euclid constrains the bizarre behavior that dark energy is allowed to have, ruling out entire families of theoretical explanations. They are systematically closing the wrong doors one by one, so we can see more clearly which single, mysterious door remains open. This painstaking process of elimination is how science corners its greatest mysteries. The solution to the quantum vacuum catastrophe may not arrive as a thunderbolt of revelation, but as a slow, gathering dawn, illuminated by the combined light of shattered particles and the ancient glow of a billion distant suns. This statistical escape route leads us directly to the multiverse hypothesis. Imagine not one universe, but a boundless, frothing ocean of them, a cosmic archipelago where each island has its own unique set of physical laws. In this vast landscape, the strength of gravity, the mass of an electron, and the value of the vacuum energy are not fixed, universal constants. They are more like local customs, varying randomly from one universe to the next. In the overwhelming majority of these universes, the vacuum energy is set to a catastrophic value. Some are torn apart by a violent big rip in their first moments, while others instantly collapse back into a singularity. But in an incomprehensibly rare few, the dial lands on a number that is infinitesimally small, a value that allows galaxies to form and stars to burn for billions of years. In this picture, our existence is not a mysterious coincidence, it is a simple selection effect. We could not possibly be having this conversation in a universe where the vacuum energy was even slightly different. We find ourselves in this particular cosmos for the same reason a fisherman finds himself standing on the one island in the archipelago that has fresh water and fertile soil. It is the only place that can support his life. This anthropic reasoning offers a kind of answer, but it is one that leaves many scientists deeply uneasy. It feels like moving the goalposts of explanation into a realm beyond our reach. If every puzzling feature of our universe can be explained away by saying we just happen to live in the one where things worked out, does that mean we have stopped looking for a real, fundamental reason? The multiverse, for all its grandeur, is currently untestable. We have no telescope that can peer into other cosmic bubbles, no experiment that can confirm their existence. It remains a powerful, speculative idea born from the mathematics of string theory and inflationary cosmology, a possible consequence of our best models. Yet its inability to be proven or disproven places it in a strange limbo, more a philosophical stance than a scientific theory. It solves the number problem by invoking an infinite lottery, but in doing so, it may have traded one mystery for another, even greater one. The vacuum catastrophe is not the only place where our physics breaks down in a storm of paradox. It finds a strange and powerful echo in the depths of space, within the event horizons of black holes. This is the black hole information paradox, a puzzle that strikes at the very meaning of reality. The problem begins with a simple quantum rule: information cannot be destroyed. Every particle carries information about its properties, its spin, its charge, its mass. In our everyday world, if you burn a book, the information in its pages is not truly lost. It is merely transformed into the complex arrangements of smoke and ash. In principle, with a perfect knowledge of physics, you could reverse the process and reconstruct the book from its ashes. Quantum mechanics insists that this principle of information conservation is universal and unbreakable. But then we have black holes. According to Einstein's general relativity, a black hole is defined only by its mass, its electric charge, and its spin. It has no other features, no hair, as physicists say. If you throw a grand piano, a collection of ancient scrolls, and a barrel of radioactive waste into a black hole, the black hole from the outside would look exactly the same. It would just be slightly more massive. All the intricate information about what fell in, the composition of the piano, the words on the scrolls, seems to be utterly and permanently erased from the universe. This is the first part of the paradox, a direct conflict between the smooth, featureless geometry of general relativity and the strict information preservation of quantum mechanics. The situation gets even stranger when we consider Stephen Hawking's great discovery. Black holes are not completely black, they slowly emit radiation and evaporate over astronomical timescales. This Hawking radiation, however, is purely thermal. It is random noise like the heat coming from a stove. It contains no information whatsoever about what fell into the black hole. So when the black hole finally evaporates completely, all that remains is this featureless thermal radiation. The information about the piano, the scrolls, and the waste is gone forever, violating a cornerstone of quantum theory. This is the paradox in its full force. Both our crisis of the vacuum and the mystery of black holes are catastrophic failures that occur at the same dangerous frontier, the point where the quantum world meets the gravitational force. The vacuum catastrophe asks how gravity reacts to the quantum energy of nothing. The information paradox asks what happens to quantum information when it encounters the ultimate gravitational trap of a black hole. They are two different manifestations of the same fundamental ignorance. Some of the most adventurous minds in physics now suspect these two problems are not just related, they may be two sides of the same coin. A radical idea known as the ER equals EPR conjecture proposes a breathtaking connection. It suggests that the fabric of spacetime itself, the arena of general relativity, is not fundamental. Instead, it may be an emergent phenomenon woven into existence by the ghostly quantum connections between particles, links known as entanglement. In this view, the empty space of the quantum vacuum and the curved geometry around a black hole are both illusions, large-scale patterns that arise from a deeper, more fundamental reality, a vast network of quantum information. Solving the information paradox would require us to understand how spacetime emerges from this quantum substrate. And if we could crack that code, if we could see how a black hole preserves information in its quantum structure, we might suddenly have the key to understanding the vacuum. We might see why the energy of that emergent spacetime is not a raging inferno, but the faintest, most delicate whisper. The tools we develop to rescue information from a black hole could be the very same tools that finally explain the quiet emptiness of our cosmos. These two great puzzles, one hidden in the void and the other locked behind an event horizon, are guiding us toward the same profound truth, a unified vision of reality where space, time, and energy are all born from a deeper, more enigmatic source. Perhaps the vacuum is not a chaotic foam, but a cosmic river of unimaginable calm. One of the most radical ideas to emerge from this crisis proposes that the fabric of spacetime itself behaves like a superfluid, a perfect liquid with absolutely zero viscosity. Think of the vacuum not as a seething, frothing ocean, but as a substance that flows without any friction whatsoever, a state of matter we can create in labs here on Earth at temperatures near absolute zero. In a superfluid, quantum effects manifest on a macroscopic scale, allowing the fluid to do impossible things, like climb up the walls of its container and flow endlessly without losing energy. Superfluid vacuum theory applies this same bizarre logic to the universe itself. It suggests that what we perceive as empty space is actually this frictionless quantum liquid, a continuous medium whose gentle, coherent motion underpins reality. In this picture, the frantic dance of virtual particles is replaced by a far more orderly, collective behavior. The very properties of this superfluid, its density and elasticity, could determine the speed of light and the nature of gravity. Constants we take for granted might simply be emergent features of this underlying liquid spacetime. This is not just a new calculation, it is a profound shift in perspective, reimagining the stage upon which the universe plays out. If the vacuum is a superfluid, then the fundamental particles we know, like electrons and quarks, might not be tiny points at all. They could be excitations in this fluid, like subtle waves traveling across its surface. Or, even more compellingly, they could be tiny vortices, whirlpools knotted into the fabric of the superfluid itself. These vortices in a superfluid are quantized, meaning they can only exist with specific, discrete amounts of rotation, a stability that could naturally explain why particles come in distinct, identical types and carry fixed amounts of charge. Your body and everything you see would not be made of solitary balls of matter, but of intricate patterns of motion within an endless, flowing medium. The promise of this radical view lies in its potential to resolve the catastrophe. The vacuum energy problem arises from summing the infinite energies of countless independent quantum oscillators at every point in space. But in a superfluid, the behavior is collective and coherent. The energy of the system is not a chaotic sum of its parts, but a property of the whole. The theory suggests that the ground state energy of this cosmic superfluid could be naturally defined and finite, potentially even zero, eliminating the infinite result from the very start. It offers a path where the vacuum's energy is not a raging, untamable beast, but a predictable, gentle feature of a unified substance. While this superfluid spacetime remains a highly speculative framework, it represents the kind of foundational rethinking the catastrophe demands. We are no longer trying to fix a broken calculation, but questioning the very nature of what we are calculating. The mystery of the quiet void is forcing us to ask if space itself is something far stranger and more structured than we ever dreamed. This deep conflict over the energy of nothing is mirrored by an equally profound struggle over the nature of time itself. Within the quiet of the vacuum lies a silent war between our two greatest theories, and time is the battlefield. In Einstein's general relativity, time is not a rigid external backdrop. It is a dynamic and malleable dimension, woven inseparably with the three dimensions of space into a single, flexible fabric called spacetime. The presence of mass and energy warps this fabric, and the flow of time itself can speed up or slow down, as proven by the precise clocks on GPS satellites. Time, in this view, is an actor in the cosmic play, a pliable entity that bends and curves. Yet, when we cross into the quantum realm, this beautiful, dynamic picture shatters. The equations of quantum mechanics treat time as an absolute and unchanging parameter, an external stage manager that ticks along independently of the quantum particles dancing on the stage. It simply flows forward, unaffected by the frantic probabilities and uncertainties of the microscopic world. This is not a minor philosophical difference. It is a fundamental incompatibility that lies at the very heart of the quest for a theory of quantum gravity. How can you successfully merge two theories if they cannot even agree on what time is? This conflict directly fuels the vacuum catastrophe. To quantize gravity, physicists attempt to apply the rules of quantum mechanics to the spacetime fabric itself. One of the most straightforward approaches, known as canonical quantum gravity, leads to a startling equation proposed by John Wheeler and Bryce DeWitt. This equation describes the quantum state of the entire universe, and it contains a bizarre and profound feature: the complete absence of time. The variable for time simply vanishes from the equation. In this timeless view of the cosmos, the universe just is, a frozen snapshot of all possible configurations. This eerie result suggests a possible solution to our energy problem. The Wheeler-DeWitt equation also implies that the total energy of the universe, when you properly account for the negative gravitational potential energy of all the masses pulling on each other, might exactly equal zero. Think of the universe as a vast cosmic bank account. The positive energy stored in matter and the quantum vacuum is like money you own, but the negative energy of the gravitational field is like a massive universal debt. The Wheeler-DeWitt equation hints that these two might cancel out perfectly, leaving a net balance of zero. This would be a beautiful, fundamental principle, a cosmic version of getting something for nothing. The entire universe could be a grand fluctuation in a perfect void, its positive and negative energies forever in balance. This would naturally solve the vacuum catastrophe by forcing the cosmological constant to be precisely zero. But the cosmos refuses this elegant escape. Our observations tell us the balance is not zero. Our cosmic bank account shows a tiny but definite positive balance, that faint whisper of dark energy driving the acceleration of the universe. The deep principle that could have resolved everything is violated by reality itself. The problem of time and the problem of the vacuum are thus tangled together in a knot of exquisite frustration. The very theories that suggest a profound reason for the energy of nothing to be zero are contradicted by the faint, undeniable push we measure in the heavens. The silent void is not just challenging our math, it is challenging our most basic understanding of change and existence. The dream of tapping into the void's boundless power has fueled science fiction for generations. Imagine a civilization that learned to draw power directly from empty space itself, a universe where every cubic centimeter of nothing becomes an infinite battery. This is the tantalizing promise of zero-point energy. The theoretical energy density is so immense that a single coffee mug of true vacuum energy could power our entire civilization for billions of years. The scale is almost godlike, offering a future free from scarcity, where starships ride the quantum foam and cities glow with light siphoned from the silent dark. Yet this glorious dream crashes against the unyielding rocks of physical law. The fundamental obstacle is the very nature of the quantum vacuum itself. This energy is not a placid lake waiting to be pumped. It is a chaotic, seething froth of virtual particles flickering in and out of existence in perfect balance. To extract usable work, you would need to break that perfect symmetry. You would have to find a way to stabilize these ghostly particles, to prevent a virtual electron and positron from annihilating each other an instant after they pop into being. It would be like trying to harness the power of a stormy sea by catching individual raindrops in mid-air, each one vanishing the moment your fingers close around it. The laws of thermodynamics present an even more profound barrier. The vacuum represents the ultimate ground state, the lowest possible energy level a system can have. Any device you build to extract energy from this ground state would itself be part of that same system. It would be like trying to use a water wheel to generate power from a lake that is already perfectly flat and level. There is no downhill flow, no gradient to drive the wheel. Creating such a gradient seems to violate the very principles that allow engines to function. Even if a clever loophole were found, the engineering challenges are beyond any foreseeable technology. It would require manipulating spacetime on scales a billion times smaller than a proton, controlling energies that could effortlessly vaporize a planet. So while the universe may be brimming with this phantom power, it appears to be locked away behind a one-way door, a cosmic trust fund we can see but never spend. This frustrating impossibility, however, underscores the staggering truth. The energy is real, its theoretical density is not in question. The very fact that such an unimaginable force is hidden in plain sight, all around us, is a constant, silent testament to the profound mystery we have yet to solve. But what if the entire catastrophe is built on a mistake? A small but significant group of physicists argue that we are not facing a genuine crisis, but chasing a phantom, a problem that only exists because of a fundamental error in our logic. Their criticism strikes at the very heart of the issue, questioning whether the vacuum energy we calculate in quantum field theory is the same energy that curves spacetime in Einstein's universe. Think of it this way: you might calculate the total thermal energy of every single molecule in the air of a sealed room. That number would be astronomically large. But if you tried to use that number to predict how much the room weighs, you would be making a category error. The random motion of air molecules does not contribute to the room's rest mass or its gravitational pull. In a similar way, these critics propose that the frantic, fluctuating energy of the quantum vacuum might be completely invisible to gravity. It could be that general relativity only responds to the average background value of energy, not to these temporary, fleeting borrowings from the void. The virtual particles that push metal plates together in the Casimir effect might simply be the wrong kind of energy to warp the cosmos. This line of thinking suggests the existence of a hidden principle, an unknown symmetry or a decoupling mechanism that protects gravity from the quantum frenzy. It is as if the vacuum energy lives in a separate, sealed account that gravity cannot access. From this perspective, the cosmological constant problem vanishes because the two numbers we are comparing, the roaring quantum calculation and the whisper-quiet cosmological observation, are describing two entirely different things. They are apples and oranges. We have been trying to balance the books using the wrong ledger. This is very much a minority view, and it comes with its own profound challenge. It requires a radical revision of how we believe gravity works. Yet it serves as a crucial reminder. The framing of the quantum vacuum catastrophe relies entirely on our current and likely incomplete theoretical paradigms. We are assuming that plugging a quantum number into a gravity equation is the correct thing to do. But our history is littered with assumptions that seemed perfectly reasonable until they were shattered by a deeper truth. The very fact that such a stark disagreement can exist among experts shows that the silence of empty space is not just a puzzle of numbers, but a battle over the fundamental rules of reality. This impasse is more than a stubborn puzzle, it is a signal. Throughout the history of science, the most profound breakthroughs have not come from tweaking old ideas, but from abandoning them entirely when they can no longer bear the weight of evidence. The quantum vacuum catastrophe carries the distinct signature of such a moment. It feels like the years just before Einstein reimagined space and time, when physicists were struggling to fix the aging framework of Newtonian physics with ever more complex and unconvincing patches. Our current situation is eerily similar. We have two magnificent, towering achievements in quantum field theory and general relativity. Each one is stunningly successful within its own domain, accurately predicting everything from the magnetic moment of an electron to the bending of starlight. Yet, when we bring them together to answer a simple question about the energy of nothing, they produce an answer that is wrong by a factor so large it defies language. This is not a minor bug, it is a fundamental system crash. It tells us that the languages these theories speak are not just different, they are mutually incomprehensible on this foundational issue. The tools that built the modern world are failing us at the edge of the void. This suggests that the solution will not be found by a clever new calculation within quantum field theory or a minor adjustment to general relativity. The path forward points toward a revolution, a complete overhaul of our conceptual vocabulary. We likely need a theory that does not see gravity as a force acting upon a quantum stage, but one that reveals how both the stage and the actors emerge from something more primitive. A successful theory of quantum gravity, like loop quantum gravity or string theory, aims to be exactly that, a new framework where spacetime itself is woven from discrete quantum threads. In such a theory, the concept of a point in space teeming with infinite energy might be meaningless from the start because there are no infinitely small points, only a fundamental granularity to reality. The vacuum energy would then be a finite, calculable property of this new quantum structure of spacetime. The catastrophe, therefore, is not a dead end. It is a brilliant beacon shining in a direction we have not yet fully traveled. It is the universe's way of telling us that our current maps, however detailed and useful, are incomplete. The greatest discoveries lie not in filling in the blank spots on our existing charts, but in realizing we have been using the wrong kind of map all along. The profound silence of empty space is a call for a new physics, one that will ultimately redefine our understanding of everything, from the smallest speck of dust to the vast, accelerating cosmos. This quiet hum we measure is the signature of a cosmos perfectly balanced on a razor's edge. Our journey has revealed a stark paradox, a universe that should be a microscopic knot of unimaginable fury, yet one we observe as a vast, gentle, and accelerating expanse. This is the core of the quantum vacuum catastrophe, a chasm between prediction and reality so vast it defies all intuition. It is the sound of two of our most brilliant theories, quantum field theory and general relativity, speaking in different tongues when they describe the void. One screams of a storm, the other whispers of a breeze. To label this a failure, however, is to misunderstand the very engine of science. This catastrophe is not a sign of collapse, but a beacon. It is a brilliantly illuminated frontier, a signpost that clearly defines the boundary between our current knowledge and the vast unknown that lies just beyond. For centuries, science has progressed by solving puzzles, but its greatest leaps come from confronting the profound mysteries that reveal the limits of our understanding. This is such a moment. The vacuum catastrophe is a testament to the raw power of the scientific method, a process that can not only build magnificent theories but also, with unflinching honesty, identify the precise points where those theories break down. It is a self-correcting mechanism on a cosmic scale. This unresolved tension now serves as a guiding star for a new generation of explorers. It points their telescopes, directs their colliders, and focuses their minds on the most fundamental questions of all. What is space, what is time, and what is the true nature of the nothing from which everything emerged? The key to reality's deepest secret is hidden within the silent, empty space that surrounds us all, waiting